Today, I will present our work on improving robotic imitation learning with predicted facial motion using transformers. Our research aims to help assistive robots perform face-related tasks more effectively. We collected facial images and landmark data to train and evaluate our models. We applied a cross-attention transformer to predict short-term human facial motions, which improved landmark prediction accuracy. Finally, we used these predicted facial motions to enhance the success rate and precision of robotic facial tasks. This diagram shows the overall system. 3 cameras provide RGB images. The transformer predicts facial landmarks from the front-facing view, and the ACT policy combines these with joint states to output joint angles for robot control. Next, I will introduce the training phase of our facial motion prediction model. We start by recording human facial videos and segmenting them into short frame sequences. For each frame, we calculate facial landmarks with a focus on the mouth region. We then combine image and landmark features using a cross-attention mechanism. Finally, the fused features are used to train a transformer model to predict short-term facial motion. Next, I will explain the deployment phase of our facial motion prediction model. During deployment, a sequence of input facial images is passed into the trained transformer. The model predicts both the next image and the facial landmarks, which are then used to guide the robot's actions. Next, we train the ACT imitation learning model. We first collect demonstration data, including joint positions and velocities, RGB images, the mouth position, and the gripper-to-mouth distance. These observations are encoded and decoded by the transformer-based ACT model to predict future action sequences. Here we show the results of facial motion prediction. The top row shows ground truth frames with mouth landmarks, and the bottom row shows the predicted frames and landmarks for approach 3. Quantitatively, the mean and variance of prediction errors in X and Y directions are much smaller for approaches 2 and 3 than for approach 1, and approach 3 also achieves the highest SSIM, indicating clearer image predictions and more accurate landmark distributions. Here we show the experimental results of the feeding task. The videos on the top demonstrate the robot performance in the linear and sampled real face motion modes. The table below summarizes the success rates under different observation settings, including baseline, current only, and current plus predicted landmarks with various horizons. In conclusion, we proposed a transformer-based facial motion prediction method integrated with ACT imitation learning for face-related robotic control. Our cross-attention model produced more accurate landmark predictions and clearer images, which improved the feeding task success rate from 42% to 74%.